Chien Hao, you can see through my camera that we have these audiences room. And I think we're almost there. You can feel free to start whenever you
Okay,
want.
sure. I'm gonna press start.
Okay. Chien Hao, do you want to speak a little bit to explain the answers to us?
Okay, sure. Okay, I'll start from the next one.
Okay.
So for this one, what is not a type of retrieval defect? So I'm referring to the paper that let me, it was yeah, retrieval defects here. And these are the bunch of retrieval defects. So the one that is not included here is a reordered document. So reordered documents, it was more of a part later where they're talking about the in context learning. Um, yeah, so that was from this slide. So for quantization, it refers to let me find the slide that talks about it. Yeah, here it refers to storing the weights of the model in a lower precision format. So instead of storing, let's say, the full 32-bit precision, we store them in something like 8-bit precision. So you lose a bit of accuracy. So you do training with the typically you do training with the full precision. And then if let's say you want to perhaps deploy it on an embedded system or like on a mobile phone where there's less memory, and then you can quantize it like that. So it'll definitely affect the accuracy of the model. But it's if you quantize it, you can also you can check how much accuracy you lose, how much loss you get from quantizing it, and if it's acceptable for the user's use case, then you can then it's okay to quantize for your purposes. So the rest are not true. Yeah, so this is from the following slide here, in context learning. So leading theories for why um there are two leading theories for why in context learning works. One is the Bayesian or kernel regression view, and one is a gradient descent as inference view. The others are I just made them up. So um, for this one, I'm looking at the paper over here. Let me find it. Um, yeah. So the paper is over here. I believe it's this one. So in this paper, so I'm going to use alpha chi here. So in this paper, um, they mention a few factors. I think some of it is in the slides. So the ordering is in the slides. So order of examples in the slides are mentioned here. That uh, with the same demos, permuting the order can swing the accuracy widely. So number of examples that also I think it quite intuitively affects the accuracy of in-context learning. Um, Proximity to the test input is something that I found in the paper, but I don't think it was mentioned in the slides. So proximity, or was it another paper? Um, yeah, I think it might be another paper online. But lastly, for the content-free entropy, um, is a is a way of measuring how balanced the distribution is. So it's a metric. It's not something that it's an outcome of the factors that affect it. So content-free entropy is not a factor that affects the accuracy of in-context learning, but rather it's a way we use to quantify in-context learning. So for residual streams, is something I can recommend a good I think uh kind of the paper that kind of explains this very well is, let me find the paper real quick. I think it's the entropic one. Let me just pull it up. The entropic has a great series on this. Yeah, so it's over here. So you can Google this, a mathematical framework for transformer circuits. It's a this paper is very good. It explains residual streams in one of the sections over here. Let me see. Yeah, so this is a residual stream. So the idea is that let me find a better picture. So the idea is that I think I'll just spend a little bit of time briefly explaining residual streams. The idea is that um instead of the entire transformer being a bunch of matrix multiplications, A times B times C times D, right? We want to have it such that there's one kind of stream over here, and each block over here, each attention block, each residual block over here, it modifies the stream by a small one. So it's instead of A times B times C times D, we do 1 plus A times 1 plus B times 1 plus C times 1 plus D. So this is a lot of benefits. First of all, for normalization, usually we kind of encourage the weights to be small. So if we encourage the weights to be small, the norm of the matrix to be small, then it means that if we send some input, by the time it hits the end, it becomes very, very small. It'll be scaled down by all the matrices. But if we do it this way, where the default, so-called the default matrix is something close to the identity, then um, the basically we can think of the entire stream here as making modifications to the input instead of making small modifications to the input instead of applying the matrix on the input and transforming it completely. So this has a few benefits. So one of the benefit is that it preserves information across multiple layers. In fact, this paper they did mention that one of the behavior they observed was that it seems like the streams because the streams tend to have a much higher dimension than the attention blocks. So we can think of the stream as like an information highway, right? Information highway like a bus, a common bus. And then these attention blocks they all read from the bus and then they process the bit of information and then they write back to the bus. So there can be some attention blocks that maybe they read like maybe um, the word he, right? And then maybe it finds what does he refer to in the previous text. Yeah, so that's one thing. It can preserve across multiple layers. So another thing is a gradient flow. So um, without going into too much detail, if you try to do gradient descent and backpropagation on a normal transformer without a stream, then it you suffer from vanishing gradients. So the first few layers, by the time you do backpropagation, the first few layers would have very small gradients. So you cannot really train the first few layers very easily. Yeah, so the first few layers would be very hard to train. But with residual streams that can be fixed. So this is also case, as I said, vanishing exploding activations, and it's not true that they eliminate the need for positional encodings. Yeah. Yeah. So for this one, I think this paper describes it very well. Also last week's presentation, there's a discussion on the QK circuits over here. Yeah, so okay, I'll use the website as an example. Um, QK. So QK. So what the QK circuit does is essentially it for every for example, if I look at the word model, right, it could mean maybe a professional model like those kind of people who wear the clothes, fashion model. It could mean a fashion model. It could also mean architecture model, or it could mean large language model. So um what a QK circuit is responsible for is responsible for um in order to contextualize this word model in the entire corpus, the queries, we will have a QK circuit mechanism where if I see a word model, then it gives rise to a bunch of questions, right? So maybe one question will be does the something like does this person walk on a runway for a living? Or does this involve a lot of weights? Or does this involve very miniature objects? So these are queries, and um, yeah, so these are queries, and then keys are the things that answer the queries. So for the previous part of the text, if let's say we see someone mention fashion, so fashion will answer each of these three questions that I have. The word fashion will answer the word fashion when I take it as a token and I embed it to get embedding vector. The embedding vector I'll multiply but with a key matrix, and that will give me a key vector. And if I dot product the key vector and the query vector, um, the how how large that dot product is represents how well that key answers that query. So if I see the word, let's say, large language, right? And then in that case, you'll answer the query of does this it'll answer queries related to AI more strongly. And from this QK from this QK from the QK circuit, it decides what are the words to pay more attention to. And then yeah, so this is how the tension head contextualizes a word.
We have 10 questions. Could you please speed up your narration a little bit in the final 2 questions? Thank you so much.
Sorry. Yeah.
Could you please speed up your narrations in the final 2 questions because we have 10 questions.
Uh, okay, so can you type in the chat because I cannot really hear that clearly. Yeah, you can type in the chat.
Oh yeah, sure.
Yeah, so just to maybe summarize in one sentence, the QK circuits gives you attention weights, which tells you where to look, and then the OV circuits they tell you they help move information around. The paper here explains it very well as well. The entropic paper. Yeah, so I think everyone got this, so I don't need to explain it. Yeah, sorry for taking up unexpected amount of time. Thank you.
Who's the winner today?
Congrats.
Yeah.
Sorry for overrunning a little bit.
No worries, and please also give Chien Hao a few hands for very responsive. Cool, great, thank you so much. It's very comprehensive. We have 10 questions today. Okay, so it's 6:20. So Prof Me and Prof Hao, they're both not here today, so it's an entirely student round class today. So I'm very excited for that. Okay. So we have 6 brilliant speakers today. So yeah, so I'd like to gently request each of you to limit your talk to 15 to 20 minutes, so that we can ensure everybody has the opportunity to talk because Dan didn't get to talk last time. So yeah, so but you're feel free to review Ben's slides last time in week 5. And yeah, so the floor is yours. But welcome, Xian. I will Xian. Keep the talk.
Hello everyone. So our main today will be looking at retrieval and reranking. Yeah. So this is a rough outline of what we are gonna do. So outside the
Xian, could you please share your screen?
oh
By the way, the slides aren't shared. Sorry, the Zoom isn't shared, the screen.
Sorry. Yeah, this one. Great. Thanks.
they ran both. So yeah, this is the outline that we're now covering for today. Yeah. And then I'll start with a little introduction of the whole part of retrieval and reranking. So a bit of a recap on Rank's pipeline. So it basically starts from doing some retrieval to retrieve documents from the data source somewhere, and then they'll pass this information to the LM. They'll do some form of magic, and then help LM to produce some outputs that answer the question. And today's part will be looking more on the retrieval. And if you recall from previous lectures, there are a lot of benefits from RAG, which includes reducing factual errors, giving better attributions and better adaptations, all these kind of things. But we know that these benefits come from the retrieval. And if we want to have all these benefits, we need to pay more attention to the retrieval. So we know garbage in, garbage out, these things that are mentioned a lot nowadays. What we feed into the LM will affect the performance. If you don't feed good enough information, it may sometimes even worsen the performance of the LM. So to gain all the benefits of RAG, we should focus, we should care about the retrieval's quality. Okay, so in a typical IR pipeline, these are the rough things that they are used. It starts from rewriting the query, doing retrieval, re-ranking, and then pass it to reader to produce the answer that you're looking for. And today's lecture focuses on the retriever and the re-ranker. So in this kind of retrieve then re-rank architecture that is adopted by most of the pipelines, the retrieval focus more on being efficient, and it may sometimes be less precise. It tries to identify a smaller set of possible candidate documents, and then pass it to re-ranker later on. So this retrieval, why it is efficient, why it needs to be efficient and maybe less precise, because sometimes you will have to process a set of documents that range from millions of documents, right? There's so many documents and the text can be so long. You cannot afford to do some very long and have computationally heavy process. And you may just need a few hundreds and thousands to quickly reduce the scope for re-ranking data. So in re-ranking, after you reduce the scope from retrieval, you can afford to be more computationally heavy here. And it's usually more powerful and it's more accurate for the task that you want to do. And yeah, so it is also very essential, this step we do, the re-ranking, because we've also learned from previous lectures that in prompting to LLMs or RAG in general, the order of the information you feed to it may matter, sometimes by quite a lot, and it will affect the quality of the generation. Okay. So an overview of what we'll cover today is these traditional IR models, which will be covered by me, and then we'll touch a bit about learning to rank architecture, the IR models using pre-trained transformers, and also, most importantly, the large language models, how it affects the information retrieval as retriever and re-ranker. Okay, so now I'll cover part on the traditional retrieval methods. Okay, so the most ancient method is this Boolean model. It's a very, I guess, simple way to model documents and queries. So documents will be modeled as a set of terms that are in the document. So you can imagine each word as a term, and you can also see them as a tag to it. And the query will be represented by a Boolean expression of terms. So imagine all these terms linked together by different Boolean terms, either be and or not, any kind of thing. So an example would be this query I'm looking for is I want term 1 and term 4, or maybe something else, term X and maybe not term 6, something like that. Okay, so a document is considered relevant to a query only if the logical implication holds. So in this example, let's say T1 and T4 in a query. If a document has includes T1 and T4, then it is considered relevant. Okay. So it does not naturally come with ranking because we see that in this model we are just directly identifying whether the document is relevant based on this Boolean terms. Okay. But there's also an extension where you can put weights onto the term and turn these Boolean connections into soft operators. So it's kind of like saying how much you want to allow when this term is true, when this term is false, whether it's relevant. It's not really just 1 and 0 anymore. So if you need more information, you can also look at the NUS IR slides, which I linked it below. So the next is on the vector space model, which pretty much just models queries and documents using vectors. And I guess this is the one that we are most familiar with. So you're just looking at different vectors, representation of the text. So it can be either binary values or maybe frequency or something like that that you count and you put it into a vector that pair one. And what we do with it is that you use similarity score between Q and E to decide the relevance. So a very basic one is TF-IDF. May not be foreign to some of you if you have taken NLP courses. So it's about term frequency, which measures how frequent a term appears in a document. And IDF, inverse document frequency, so it's the inverse of how a term appears in other documents. So it measures the relative importance of the term. And TF-IDF is a product of these two metrics. So together, they reflect the significance of the term within the document relative to a collection of documents. So there are some problems with TF-IDF. So for example, it may over-reward repeated terms. If you have terms that are repeatedly mentioned in the text, may give higher values. And also often TF-IDF will do some form of normalization based on the document's length. So it may over-penalize when the text is too long. So later on, people invented this BN25, which has the formula over here. Okay, so, this IDF and a bunch of things over there. So basically, what it incorporated is that it takes care of term frequency better. It ensures that there's no over rewarding for repeated terms. And if you look at if you look at the formula, the F times Fk plus 1 over F plus K something, it will tend to a constant when the terms keeps getting repeated, when the frequency is high. So yeah. And there's also a part where it handles the length of the document better by doing the D length of D over the average document length. So it kind of like measured your document's length compared to other documents. So this is still a strong baseline model even until now. And the next is about probabilistic models. So given a query, you want to rank document by how likely they are to be relevant. So this is also the formula they use for this classic model, which is the binary independence model. It assumes that terms are independent and a bunch of other assumptions. And basically, this is the formula that it works with. And the intuition is that it measures the odds of seeing the term in relevant documents over the odds in the terms is in non-relevant documents. So it kind of gives you a score of showing how likely the document is relevant to a query. Yeah. Okay. So all these traditional models have certain characteristics. Is basically that they are ultimately heuristic based and sometimes statistically based. So it still relies on the exact word match. It also means that there's no semantic consideration. It doesn't understand semantic meanings of the text. And also when you try to change the language, then you may not be able to get a match, right? if it's the same. So naturally we need better ways, and they'll be covered in the next few sections. These models that I mentioned earlier also considered as fast retrieval because the vectors tend to be sparser. Yeah. Okay. These are also generally fast and less computationally heavy. And sometimes people may use it in conjunction with other methods like dense retrieval and make it a hybrid retrieval to boost it further. So yeah, that's all for my part.
Anyone have questions for Ming? Feel free to ask questions. Anyone have questions? Yeah, so maybe I have a quick question. So, what does Bi-Encoder BM stands for?
Yes, actually. I'm not sure why it's not. Okay.
Yeah, I vaguely remember that BM just means better matching or something. So,
Yeah,
that's it. Yeah, thank you so much.
What about the 25?
Yes, what about 25?
That I don't know.
Right, so next we're going to cover the formulation of ranking as a supervised ML, generally known as learned rank. So basically, the data set we have is composed of a bunch of tuples of queries and documents and relevant labels. So each relevant label tells you how relevant the given document is to the given query. So generally how this proceeds is first to extract features from your query and your document, and then you train your ranker to approximate the relevance label based on the feature vector. So the methods for extracting features and ranking are what we're really going to be covering next. Right, so first of all, there are a number of different approaches to LTR, pointwise, pairwise, and listwise. First approach, pointwise, takes in one document at a time and outputs the feature vector, which is then used to compute similarity with the query. And notably, this feature vector is computed independently of the query and independently of the other documents. So obviously, there's a lot of information that you'll probably be missing out on by this approach. However, despite that limitation, this has achieved surprising success. So let me work on pointwise learning to rank, mostly applied regression-based techniques. So given the relevance label, which usually is a number describing how relevant the document is to a query, you might be tempted to formulate it as a least squares regression problem. However, it turns out that since the relevance labels are generally qualitative judgments where the ground truth is supplied by humans, so my relevance score being the relevance score given by me being 0.5 might not be the same, might not actually represent the same degree of relevance as someone else giving it 0.5 relevance score. So since this yi is actually a qualitative judgment, it does not make sense to train a computer to predict it exactly as if it were a quantitative one. In fact, in practice, yi actually tends to take on discrete values. For instance, 0 being irrelevant and 1 being relevant, or in other surveys that you might see, ranking relevance on a scale of 0 to 4. So we have 5 scales, we have values, 5 discrete scale of values, 0, 1, 2, 3, 4. So a classification-based approach to pointwise LTR actually tends to make more sense in this situation. So there are, again, a number of formulations of pointwise LTR as a classification problem. So when yi is simply a binary label where 0 denotes irrelevant and 1 denotes relevant, you can formulate it as a binary classification problem where the label is approximated by a classic binary classification method such as support vector machine or maximum entropy, or basically any other model you can think of. However, most papers fall into the multi-class classification category, where a document is classified into one of usually 5 ordinal categories, where each class corresponds to a certain degree of relevance in increasing order. And to rank documents by their relevance to the query, you simply classify them and then rank the documents. Documents assigned to the same relevance class are generally ranked arbitrarily. So as an example here, this paper called MC Rank uses gradient boosting trees as classifiers. So basically any multi-class classification model will work if you solve it into this approach. And so a third approach to pointwise learning to rank is something called ordinal regression. So you define a set of disjoint intervals on the real line, each of which represent categories in increasing order of relevance. So yeah, if the model's output falls into interval number J, that means the document that you pass into the model is going to go into relevance category J. It's a very nice illustration of it here. And so one notable approach to ordinal regression-based pointwise LTR is p-ranking, which is basically perceptron-based ranking. It uses the perceptron algorithm to update each AMI. And it does this by first initializing the perceptron weights as null. And then for each sample, you predict the rank as the minimum k such that xi will fall into the intervals vk and up. And you calculate the error set as basically all the thresholds which are too high. And then you rotate the hyperplane defined by W as in the original perceptron algorithm. And you also decrement the thresholds that you have deemed to be too high by the error set. So here's the diagram describing the basic intuition, the p-rank algorithm. There is also another paper that uses a support vector machine for ranking that uses the SVM to update these thresholds. And they propose an alternative approach where the thresholds don't necessarily unite to form the whole real line, but instead the categories, both endpoints, are adjustable and learnable and optimized for. And in this formula, the interval representing class J is as described over there. And recall that the SVM seeks a maximum margin hyperplane between two disjoint classes. So to maximize the margin, you maximize the distance between neighboring intervals, or in other words, minimize this expression. Yeah. And as in the original SVM algorithm, the epsilons here penalize the data points that lie within margins or are misclassified. So the pointwise approach is more computationally efficient because you're only considering each document in isolation. However, it doesn't directly optimize for the correctness of the relative ordering, which is actually what the ranking task is all about. So the pairwise and listwise approaches seek to fix it. First of all, pairwise. Given the query and two documents, you predict which document is more relevant, or more precisely, you train a model to predict which document is more relevant to the query. And while this takes into account relative ordering between pairs of documents, it does not quite optimize for list-based evaluation metrics. Despite that, it is still a step in the right direction, as we're going to see. So ranking SVM uses SVM-based method, but instead of the SVM taking in single feature vectors per document at input, it uses the SVM to minimize the number of pairs that are wrongly ordered. So from your ground truth data set, from the ranking, you can derive a set of pairs where the pair P, Q means document P is ranked higher than document Q. And so you can very easily convert the list data set to a pair data set, and so convert it to the right form to fit into the algorithm. And the intuition behind this formula here is that the vector xi minus xj is going to be classified into one of two half spaces, as in the original SVM algorithm. So if I is ranked higher than j, then it goes into one half space. If j is ranked higher than I, then it goes into another disjoint half space. And yeah, so next we have RankNet, which optimizes a binary cost function. So suppose we have access to the ground truth probability that xi is ranked higher than xj, which you can obtain from the ground truth ranking list. Then your model takes in individually xi and xj and computes the difference between them and squishes it using a sigmoid function. And as we all know, the sigmoid function very conveniently compresses all its inputs to the range to the open interval 0,1, which very conveniently gives us a probability score. And when we have two probabilities and we want to minimize the divergence between them, very conveniently we use the cross entropy cost function. as our optimization objective. And interestingly, notice that the network only actually ever operates on one single sample, but the pairwise coupling is only performed during the optimization step. Another method is lambda rank, which tries to address the problem that list-based metrics generally operate on the discrete ranking indices assigned by the model to each document, and therefore are generally not differentiable. So what the lambda rank authors do is they formulate a rough approximation for the gradient of the list-based metric with respect to the ranker outputs. And if you have the gradient of the list metric with respect to the ranker output, then by chain rule, you can compute the gradient of the list-based metrics with respect to your model parameters and update the model accordingly. So very nice. Yeah, and they tried over 10 different approximations and eventually settled on the gradient of the loss used by RankNet scaled by the increase in the normalized distributed cumulative gain of swapping a certain pair. So a neat part about this algorithm is that the comparison, despite being pairwise, indirectly optimizes for the list-based metric all the same. But what if we could just optimize the entire list-based metric directly? So that is what the list-wise approach tries to do. And our first example, soft rank, optimizes a smooth approximation to NDCG. So since the rank of each document is going to be treated as a discrete index anyway, which is kind of what makes the whole NDCG computation non-differentiable. What if we decided to smooth it into a normal distribution instead, where our standard deviation is some hyperparameter that we can pick? Then it turns out that the probability distribution of sub-document U being ranked higher than document B can be calculated as this expression, which, since it's an integral of the Gaussian function, it's smooth. And now consider what happens when we add the documents one by one to the rank list. So when we add a new document, the existing documents that are ranked below it are going to shift the ranks downwards by one, while everything that's ranked above it is going to keep its rank. So this is what we use to formulate a very nice recurrence relation that gives us the final probability of some document landing at some rank. So essentially, there are two ways for some document to end up in rank R. Either it was overtaken by, either it used to be at rank R-1, but it was overtaken by some newly added document, or it was already at rank R and the newly added documents turned out to be ranked below it, so its rank remains safe. Yes, and so through this recurrence relation, by adding the documents one by one, by simulating the one by one addition of documents to the rank list, we can get a smooth approximation of the probability that some document lies at some rank. And since this approximation is smooth, and we can use it to calculate NDCG, why not just calculate NDCG by this thing? And since our smooth approximation to NDCG is directly optimizable by gradient ascent, we can just optimize it and we are done. So that's quite a pretty method. Next, another approach to approximating list-wise metrics is lambda mat, where the lambda rank approach is used to approximate the NDCG gradients, but instead the authors use a different feature extractor to approximate the gradients, called MAT, which is a regression tree, a gradient boosted regression tree. Yeah. If anyone needs a quick recap on regression on decision trees, basically the intuition is they kind of partition the input space into a bunch of disjoint cells and assign a scalar output to each cell. Yeah. So another list-wise LTR approach is called set rank. The chief advantage of this method is that it is permutation invariant by nature of using self-attention without positional embeddings. Recall that self-attention, that the attention mechanism is invariant to the order of tokens in the query key and value. And so if you don't deliberately inject positional information, this whole thing is going to be is going to be positioned invariant. So when you are asked to rank a set of documents in relation to a query, it doesn't matter what order the document you are given the documents in. And so your algorithm, of course, should reflect that. And that is exactly what setrank seeks to do by using self-attention. So all input embeddings are passed through a bunch of multi-head self-attention layers and then projected down via FFN to a scalar. So each document gets a scalar relevance score to its respective query. And apart from modeling the query document interaction in a permutation invariant way, using multi-head self-attention also allows you to model the pairwise interactions between all heads of documents, which, when you consider that ranking is about determining the relative importance of the documents in relation to the query, is quite important. It's nice to note that if you have another ranker that approximates your final ranking in perhaps a more primitive way, you can maybe choose to include the prior information by adding what they call an ordinal embedding to your input embeddings before feeding it to the multi-head self-attention layer. So now we're going to go on to the different kinds of neural network-based methods used for learning learning to rank. So in contrast to the traditional methods brought up by my previous presenter, neural LTR ranks by semantic similarity rather than exact text matching, by virtue of operating on text embeddings rather than handcrafted features based on exact terms. So there are a number of methods for neural LTR. One is representation-based, where you train a model to encode both your query and your document into a shared vector space, and then compute a similarity metric between the embedding output for the query and the document. The formal mathematical specification is here. Another slightly more performant method is the interaction-based method, where one model takes in both query and document and directly outputs its relevant result. And while it's more accurate, it's more computationally intensive because generally all your features in Q will interact with all your features in D. And if you have, say, 100 words in your query and 100 words in your document, that works out to like 10,000 similarity scores you have to calculate, which isn't great. Another approach is hybrid, which combines both interaction-based and representation-based methods. So recently you might have heard about modern LLMs repurposed for embedding and re-ranking, and these fall into the categories of representation and interaction-based LTR respectively. And in this section, we are going to focus on earlier work with less advanced neural network architectures before transformers. Transformer-based LTR methods will be covered by a later presenter. So first of all, our first representation-based neural LTR method is the deep structured semantic model, or DSSN, which breaks documents into successive n-grams of letters and represents them by a multi-hot vector, where the component is 1 if it contains this corresponding n-gram and 0 otherwise. And this multi-hot vector, or hash, is then compressed into a 1 to 8 dimensional vector by a Fourier NLP. And to compute the relevance between queries and documents, they simply use the canonical similarity measure of cosine similarity. And since DSSN was trained on click-through data from search engines, the determination of whether the ground truth value of whether document D is relevant to query Q is very simple. You just check if the user clicked on document D after asking query Q. So this is the objective that DSSN used, which essentially seeks to maximize the likelihood of outputting the relevant document while minimizing the likelihood of outputting an irrelevant document. You're going to see this objective function a lot in later slides because it's extremely generalized. So later work swapped out the NLP and DSSN for more advanced architectures such as CNNs and LSTMs. So the convolutional DSSN, instead of encoding entire documents into hashes, they encode each word into a hash, then perform 1D convolution over the word sequence. The final representation of each document is derived by max pooling over the sequence dimension. And the sliding window approach allows the CNN to, by virtue of its receptive field over multiple sequence elements, it can learn representations of n-grams as well as phrases spanning multiple words. So in a similar vein, DSSN can also be augmented by a log short-term memory model, better known as LSTM. And similar to the convolutional DSSN, they hash each word into a letter n-gram hash, and then feed the resulting per document sequence into the LSTM. And LSTM is generally capable of modeling longer range dependencies than both MLPs and 1D CINs by maintaining an internal representation of every token, every word representation that is previously seen. And this improves upon the fixed receptive field of the 1D CIN. Note that while LSTM is somewhat better at modeling long-range dependencies, it's not quite good enough for the memory to be retained over tokens that are hundreds of thousands of sequences long. So that will be transformers, and those will be covered later. So on to interaction-based neural LTR. Our first method is match pyramid, which computes an interaction matrix between all words in the query and all words in the document. And since this matrix is two-dimensional, it's natural to use image-based ML methods such as 2D CNN on it. So first, they take every word in the query and document and embed it via word defect. And the I, J entry of the interaction matrix is simply the cosine similarity between the word defect embedding of the ith word in the query and the jth word in the document. So first of all, they feed the interaction matrix into a 2D CNN and then followed by max pooling, and then just the usual flattening the feature map and then passing it to an NLP. And then the binary classifier predicts whether the document is relevant to the query or not. And similarly to the convolutional DSSN, using the 2D CNN over the entire interaction matrix enables modeling of interface dependencies between the query and documents, and it's because your CNN's receptive field can span multiple tokens in both query and document. And interestingly, this method avoids the locality bias that is often quoted of CNNs, because the filter actually slides over all possible pair of words in Q and D by virtue of the structure of the interaction matrix. So it's strangely reminiscent of the attention matrix. Yeah. Next, we have the deep relevance matching model, which in part uses the interaction matrix as computed in the previous method, but instead aggregates rows into histograms. So every document is basically just treated as a bag of words. And the authors claim that the relative order of words in the document is simply noise and doesn't quite contribute to the final ranking measure. I'm not so sure about that, but their performance numbers seem to indicate them. So yeah. So they group the document terms into the bins of the histogram based on the cosine similarity score with each term in the query. And finally, they feed this histogram into an NLP, which learns the contributions of each bit of the histogram to the final relevance score. So finally, we have hybrid methods, which combine both representation and interaction-based neural LTR. And the one method we'll present on is called DUET, which sums scores from the representation and interaction-based models. So for the representation module, they take a 1D CNN that similarly consumes word hashes from query and document, and at the end they combine the query with the document output by element-wise multiplication and project it down to a scale score. And the interaction-based method, similarly to match pyramid, is a 2D CNN that simply slides over the query document interaction matrix. So what the authors found was that the hybrid method of duet clearly outperformed both the representation only and interaction only methods, which speaks volumes as to the effectiveness of combining both. Yeah. Now I'll hand over the time to our next presenter. Thank you very much.
For this section, I'll be talking about contrievers as retrievers, and contrivers are unsupervised retrieval method. So for contrivers as retrieval, we have three methods used over here. The first method is random copying, which generates the positive and negative examples for our contrivers. And we have momentum contrast, which is a cue used for the negative examples. And we also have contrastive learning, which is used as a contrastive loss for the contriver. After that, I'll be talking about hypothetical document embeddings, which is used in contrast with contrivers to retrieve documents accurately. And we have retrieve and plug method, which can integrate the contriver for supervised for large language model fine-tuning. So for independent copying, we will sample two independent spans of text, and for a single document, we will generate two positive pairs. So this positive pairs, since they're coming from the same document, they are seen as related. And for all other spans of text that are found from the other documents, they are seen as negative pairs because they are coming from a different document, so they are likely to be not related. And a positive pair is used for contrastive learning, and so the model will be taught to see them as related. And since what we are doing here is by sampling two random spans of text, there's a possibility of the overlap between the two texts. And so this teaches the model that there is some kind of matching in between words. And this is analogous to like EM25, where we use like skill matching. And this we also use like additional data augmentation methods like random word relation, replacement, masking positive pairs. And this will generalize the positive examples. So for momentum contrast, we have first what we do is that we compare the positive query to the negative positive query and the positive key. And this will generate the contrastive loss, and it will fit that into the encoder. And after that, we will maintain the negative, we will maintain the negative keys in a queue as well. And so the negative examples will be dequeued from the queue, and then will be compared with the positive key here. And this will generate the contrastive loss to the encoder. And why we have a queue here is that with a larger queue, we will be able to maintain a larger examples of negative text. And so with the larger amount of negative examples, we'll be able to generalize these examples so that the model will be more accurate. And for this part, the momentum encoder is an encoder that is updated separately to the main encoder. And this updates through a moving average process. Since we have a queue with a large number of negative examples, we want to make sure that they are accurate and up to date. And what we do is that we update the momentum encoder slowly so that the positive and negative examples can be compared. Yeah. And since the momentum encoder is also updated gradually, we will dequeue the old examples and queue the new examples so that they remain relevant. And from this, we'll compute the contrastive loss. And the contrastive loss here is that the loss function that you see over here. Basically, it uses the similarity score by computing this over here, the dot product, and then it uses the temperature parameter as well to compute it. So this loss function is used in a lot of contrastive learning. And for this case, the authors use this version of loss function. And why this is good is because by using unsupervised learning, we can train a large set of, by using unsupervised learning, we can train our data sets, which are originally in English, right? But then, by allowing it to train on dense retrievers, you'll be able to, sorry. So while large labeled data sets are available in English, allowing to train strong dense retrievers, this is not the case for lower resource languages. So for example, if we have a very niche language like Arabic, it might not come with a lot of labeled data sets. And this is where we want to use things like unsupervised learning for this. And this works for cross-lingual retrieval as well. By retrieving documents like English documents from other queries of a different language, we'll be able to use this. And so one instance is by retrieving English documents from Arabic queries, which will not be possible when using things like lexical matching methods using BM25. And how we can improve the retrieval with a contriever is by asking the large language model to generate a hypothetical document by writing an instruction like write a document that answers the question. And by creating such a hypothetical document, we'll be able to pass it into the contriever and retrieve a real document. How this works is that we have a lot of positive documents over here, and the query lies far away from the positive documents. So by generating a document, our document will be more semantically featured than the original query. And this will allow the our document to lie closer to the positive documents. And what we can do over here is to generate multiple sets of hypothetical documents and finding the average of the embedding. And by doing that, we'll be able to compute the similarity score for this. And why the contriever works here is that because the contriever acts as a dense bottleneck and will serve as a compressor. And this will put out the hallucinated details from the embedding as well. And with this, we can see that using the contriever will provide us with marginal performance over the BM25. But when using height, we can see that it's improved for unsupervised learning. And even in some cases, height will perform better than some of the supervised learning methods. And moving on, we have replug as well. So replug is what we have with replug is that we see the LLM as a black box for retrieval. And replug retrieves relevant documents using an off-the-shelf retrieval model and are pre-blended to the input text context and fed into the black box LLM to make the final prediction. So what is happening over here is that we have an input context, and the input context is being passed into the retriever. And the retriever will retrieve some of the documents. In this stage, the retrieved documents and the input context will be concatenated and passed into the LLM black box. And this will be done in parallel for all of the retrieved documents. And from this, we'll generate some of the probabilities over here. And we'll combine the probabilities and find the most probable output for this, and we'll output that result from the black box LLM. And by extending this idea to LLM supervised retrieval, here we will tune the retriever, which is the contriever in this case. So in the first step, we'll, just like before, we will pass in the context into the retriever. And from the retriever, we will compute the retrieval likelihood, which is the formula found here. In this case, we'll use the cosine distance and hyperparameter, which is the temperature of the softmax. And next, we'll also compute the LM likelihood, which is the same idea as the retrieval likelihood, but just that here we are using the likelihood from the large language model. And by combining these two distributions, you'll use a Kell divergence to compare the distributions between the two models. So in this case, the Kell divergence is telling us that we are trying to match the distribution of the retriever to the distribution of the large language model. And this is used as a loss for the retriever to update the parameters. And since the retriever is also updating as it is being fine-tuned, the data store index will be updated. And so what we are doing here is every t training sets will update the data store index. And from this, you can see that using replug has improved performance over the Contriever, and by fine-tuning the Contriever using the language model supervised retrieval method, there's a slight improvement as well. And next, I'll pass on the time to Estelle.
Hi, so thank you so much for Swislar. Let's give Swislar a quick hands. Yeah, so please, class as we can have a short break for bathroom break for 5 minutes. We'll come back later. Five minutes and we keep it continuing with yeah, so you can be finished by yeah. But I don't know. Do you guys think that I think I can finish in the second half have a balance on that? I think this person was yeah, that's like the it's that I never know, but that's right. Yeah, I get this in this.
It's very common. Yeah. I think most has it is really for people maybe go in the shapes of our teams.
So, hey guys, alright. So yeah, we're back after a quick break. We'll go resume our next second half of the lecture. So let's give Estelle that out.
So covering Bi-Encoders and Cross-Encoder. So why use Bi-Encoders for information retrieval, less retrieval, fast retrieval, multi-vector, and cross-encoders? So cross-encoders are an interaction-based model. It uses a concatenation of the query and document to calculate a relevant score. A Bi-Encoder independently encodes the query and document and then calculates the similarity score, which allows for pre-computation at the cost of some contextual loss, because not everything in the query and document are computed against each other. And this is commonly used in large-scale information retrieval because we don't want to compute the query against every document in the dataset of say 50 million. So we'll start with dense passage retrieval. You see the contrasted loss again. It learns a representation space of documents by contrastive learning. So there's no cross-attention between query and document, and it is a trade-off between efficiency and expressiveness, which we'll see a lot in this section. As an aside, here is Simon's bird training. It's trained with cross-entropy loss on the SNLI dataset, and with regression loss, which was mean squared error on cosine similarity on the semantic text similarity dataset. So as we see in the result, it captures sentiment information, but there is domain generalization issues because it does not compute as expressive of a similarity metric as some other more advanced methods do. So we see that the dense retrieval generally outperforms BM25 as expected. As we look here, the documents retrieve are qualitatively different. In the first example, it's a true positive passage retrieved by BM25. So we see that England and Ireland. So the first one is false. England and Ireland appear in the passage and service retrieved, but it's not actually referring to the body of water. But in the passage retrieved by dense passage retrieval, we see that it mentions the Irish Sea, the North Channel between Scotland and Northern Ireland. And so presumably this is more semantically close, even though it does not necessarily include as many of the keywords. In the correct passage retrieved by BM25, it directly mentions Game of Thrones, and in the wrong passage retrieved by DPR, it's supposedly semantically similar, but does not include specific keywords because these keywords are important for retrieval, what we call long-tail talking. So I'll move to approximate nearest neighbor for information retrieval. Except nearest neighbor search is costly, and approximating this can reduce query latency and is faster than doing the exact search. Here are some strategies we covered before. So this allowed for doing negative contrastive estimation, or ANC. Negatives are often too easy during trainings, and because most negatives are too easy, in-batch negatives are often also too easy, and so the model plateaus. ANC draws negatives from a global ANN index, which is recomputed periodically. It actually approaches cross-encoder rerankers using only dot product similarity. Here is a proof of the convergence rate. So we have the SGD step here. Then we can derive this expression for SGD progress, and we have to step that at various penalties. We consider the second moment, and we can find this optimal distribution. Derivation is shown here. So the optimal distribution is proportional to grad norm. So large grad norm examples are weighted more. This shows that we should use informative negative examples, and intuitively, these prefer to have negatives. In EMCE, they retrieve this by recomputing the ANN index. Because as the model improves and its embedding space changes, what are hard negatives also change. This avoids negative stagnation. In EMCE, they show that retrieval can be improved without an increased inference cost. So their main contribution shows that improving the training can improve retrieval. And by providing better negatives during contrastive learning, we can approach cross-encoder expressiveness with only dot product matching. As we can see in training loss and the grad norm at various layers of the model, it increases grad norm and converges more quickly. So it reduces overfitting to the trivial distinctions between positives and trivial negatives. We'll move on to sparse retrieval. Sparse retrieval gives high-dimensional, mostly zero vectors, and these non-zeros correspond to the feature set. The similarity measure can be quite many things. Often it is inner product or weighted overlap. So it does better on exact term matching because it has more expressiveness in the higher dimensional space and better long tail recall. But it uses much larger vectors as well and has limited semantic generalizability because dense retrieval learns an embedding space directly, and sparse retrieval may do worse on this. We'll first discuss the mass language model being used in sparse retrieval. A very important paper in this field was made. So this predicts the term importance over word piece vocabulary. It computes the importances using a math language model. So at every point, it calculates the term importance of every vocabulary item in word piece. So by doing this, it expands so that not only terms present in the query or present in the document are included in the representation. And then it uses these importances in WIJ, and it uses the log saturation to dampen the very large weights. Then we sum over all inputs, because supposedly the order does not matter. This fast representation is also done by contrastive learning and flux regularization. Flux regularization applies this penalty of retrieval time by approximating the activation probabilities. These activation probabilities, as you can see, encourage sparsity by pushing many of these to zero. Because we probably want small query sparsity to improve on search time and the embedding space, we use separate regularization on the query and documents.
Why not?
In the implementation of rank IDN, we use in-batch negatives and only one hard negative retrieved from BM5. So in split V2, they change some pooling to max pooling. Intuitively, this picks a stronger signal and there's less dilution of strong terms. But it's from empirical evidence with split, and I recall there were some papers in which it did not in fact produce improvement. They also use distillation learning, which we'll cover. As you can see here, distillation split does very well on the mean reciprocal rank. And on the right here, see a comparison between split and split doc. So split doc had no query embedding, and it only uses the dot product between token occurrences and document embeddings. So this is a lot faster for search. Here's the distillation learning process for split P2. They did distillation learning from a cross-encoder reranker with the 3 million parameters. And in doing this, they first trained a split retrieval and the cross-encoder reranker. Then they generate triplets from the distilled split, and the reranker generates scores. Following which, they use this MSE to create split again from scratch and got rid of regularization as discussed before. Doing knowledge distillation from the reranker this way gives more informative examples. So as we see before, this improves convergence. Onto multi-vector representations. It represents inputs by using many vectors and better captures fine-grained relevance. Because these vectors may be splitting the document into topics, rare terms, or different parts in semantic information. Here we use best similarity instead of cosine sim for dense models. And we have the expression here. Doing this pairwise exhaustively is very expensive. So as we show, there can be H&S W, there can be clear estimations as we discussed, and token pooling. Still, this usually has higher storage and retrieval overhead, and doing such approximation may reduce fidelity gains if not done well. Instead of doing all-to-all interaction, we can do the interaction for reranking and indexing. So this still captures semantically rich interactions, but doing it only at the late stage after some attention on Korean documents allows for fast vector similarity. This also allows us to use inverted file with product quantization as with sparse retrieval. So it searches the nearest p partitions, which is much less than the total, and it concurrently retrieves n times k prime documents where k prime is less than k, and big K unique are the only ones we have to rerank. So it greatly decreases the amount of documents we have to rerank. Colbert does fast re-ranking of the top 1000 BM25 results, and yeah, we have very high retrieval recall. Over here, we see the latency of this is much less than using a full BERT model. So it's 458. We can do a lot better. For dissertation learning in Cobalt, they use scale divergence loss and 64 weight tables, so this is very expensive. After training the initial Cobalt model with triples, they get the soft probabilities from the teacher as with an early model we discussed. And KL diff loss intuitively helps denoise by giving more expressive labels instead of just 0, 1. So this helps with generalization, and it imitates the 22 million parameter cross-encoder scoring behavior. This generalizes much better on all of distribution tasks, as we see on the right. So with this, it is timed the best on all of distribution and long-tail task verified evaluation tasks. We observe that covert vectors cluster into specific token semantics. So we can represent these vectors as centered plus a residual. And the residual vector can then be quantized to very low bit precision because these are close to the centroid. So it preserves the linear interaction expressiveness while being much more scalable. In play, we do not exhaust the space for candidate passages. So it's only done on centroid first. And it already contains most documents from the full covert retrieval strategy. We start with candidate generation, so we find query similarity to the central vector. We use k-means to find an initial candidate set, and this only stores the map from central to passage items. So we also save on storage. Central interaction then skips the embedding reconstruction for almost all passages. We just look at central approximate scores and look at the top k dots. After that, we prove the low score centroids. And this selects only n dots over 4 documents. And finally, we only have to re-rank n dots over 4 documents. So that saves a lot on the re-ranking. Also, because MaxSim has most of its time spent on tensor reshape and padding, they implemented C++ CPU kernels to improve computation, and they do pre-computation of index list in a lookup table for faster lookup. We see that the latency here on the CPU even improved greatly without much decrease in recall. So it's a very big improvement from the vanilla Cobalt v2. Can we do better? We have late interactions, providing an effectiveness and efficiency trade-off. So now we can further improve this by adapting the MLM head to covert P2 with only 0.6 trainable parameters. So we don't need the 22 billion parameters. We use the same representations for retrieval and ranking, but we can further replace back of centrals with traditional sparse retrieval. So the candidate generation is directly in the vocabulary space instead of the representation, which is also more we get 3 millisecond latency for this. So there's a very large improvement. Finally, we'll move on to cross-encoders for re-ranking. And re-ranking is useful not only with the M25 lexical retrieval, as a lot of papers tend to do, but as strong first-stage retrievals approach naive re-ranking. Many of these retrieved documents are already very good. So with stronger retrieval, we can re-rank. We can decrease the re-ranking depth without much performance drop. And because we have diminishing returns for re-ranking depth, we want to use as small a depth as possible, where we still have an effective model. I'll discuss task-aware retrieval, where user intents are not fully captured in query-only and Bi-Encoders. So a cross-encoder is more expressive at the cost of doing this for everything. This model is trained with cross-entropy loss again. 90% of the negatives are randomly sampled and 10% are sampled from Contriever and instruction unfollowing regimes. This better captures the user intent in an open domain environment, so it generalizes much better. By concatenating the task, query, and document, it outperforms much larger models. And it requires only one human written instruction to adapt to new task. No additional data generation is required, so this also helps with training. Instruction tuning then helps a lot with retrieval, as we see here. And this is only 1.5 billion parameters compared to a lot of the larger cross-encoder models. Because cross-encoders are accurate but so expensive, we can do similarity-based early exit. This is a heuristic-based approach, which avoids doing the full computation. So there's no modification to the models, and it only does similarity scores using some of these attacks. By using token embedding similarity at early transformer layers, we don't need complete computation. Here is recall versus where we apply this in the transformer blocks. Using early layers to prove may be too early, but lexical meaning and shadow semantic meaning are used in proving an earlier layer. But it's a tunable threshold, so we can prune later to degrade performance less. So it really depends. We also observe that maxim does the best here. Similar reason. I'll pass the
Hey guys, I will introduce using LLM as a retriever. So this is the outline. So I will first introduce why we need LLM as a retriever. And then the second paper I just noticed that has been explained by the previous presenter, so I will probably skip it. And I will explain two interesting paper in this field. So why do we need LLM as a retriever? And before answering that, I would just give a formal definition. So how does LLM as retriever works? The input is a query, and we send that query to LLM, and then we use the generated information as the retrieved information. And what are the benefits of it? So LLM can act as a zero-shot retrievers without the need of training data, because it has already been trained by a lot of context. And they also enable task-aware retrieval, because the task might also include it in the pre-training context. And they can handle query reformulation and expansion, such as rewriting the query. So this will improve the recall. And they can serve as teachers or judges to generate synthetic data as label to train smaller retrievers. And also they can serve as a unified system. So you don't have to build a very complex search system. So you can just give the query to LLM and then use the generated information. So I will skip this paper. And I will explain this paper first. The large language model strong zero-shot retriever. So this is actually built upon the previous one, the height one. So their motivation is that the classic zero-shot retrievers, they usually perform comparative or worse than the BN25. And LM seems promising because it has a large amount of retraining data, but simply prompting it to generate hallucination or out of domain or misleading answers. So here is the method. So what they do is that they first use a query to use BN25 to retrieve some candidates, and then they give the candidates to the LM to generate some answers. So why this help? Because if we have some candidates serving as an example to the LM, so the LM might have the sense like what kind of pattern you are expecting to retrieve. So this helps generate the pseudo answer, as called, and then they use the generated answer to serve as another query to use BN25 to retrieve the results. And here are the experiments. So we can see that this simple method to just use BN25 to retrieve some candidates, it outperformed the previous height method. And what are the interesting findings? So the first one is that the initial retrieve candidate methods, because it provides a pattern for the LM to follow. And then using the LM to generate pseudo answer is better than asking it to rewrite a query, because the pseudo answer might have richer semantic information than the rewrite query. But this also has some limitations, such as the long inputs, and also they don't have the very domain-specific queries informations. And this is another very interesting paper, and it has been getting a lot of attention recently, and it's called Search R1. So they train the LM to reason and leverage the search engine with reinforcement learning. So this work, they don't use LM directly as a retriever to use its generated information, but they rather train the LM to interact with the search engine. So how they train it? They first provide a template for the LM to follow. This can be done just by prompting. So they need to have the think token that the LM need to reason what kind of information you might need to search online. And then they have a search token. So they will provide the search query between this search token. And then they have the information token, which the retrieved information will be put into this token. And then they answer about the question. So this LM would follow this format first. And then they use the regular reinforcement learning algorithm, such as the proximal preference optimization and group relative preference optimization. Maybe I will just explain one, the GRPO. So how they do is that given a question, the rollout module is basically the LM and the search engine. they interact together to following the previous template that generates multiple responses. And then they use a reward model to kind of give a reward to each of the response. So the reward would just be to check whether the generated answer match with the ground truth answer. And then they have a reward for each response. And then they compute the relative advantage between those rewards, and they get the advantage score for each of the generation. And then they use that score to update the LM. So the LM during this training, it can learn how to interact with the search engine. And after training, how they do the inference. So it's quite straightforward. So they first roll out some sequence, which is the response, and then they generate some response token, and then to see whether they have search token or answer token. And if they found search token, they will do the searching, and then they put the retrieved information between the information token, and then they use that retrieved content to give the answer. And if the information is not sufficient to give the answer, they repeat the loop to search and reason again until they find the final answer. And this has a very strong improvement compared to all the previous methods. And yes, so this is the end of my sharing. Thank you.
Guys have questions for Jundong? Feel free to ask questions.
Yeah.
People online, do you have questions for Jundong? Okay, so if no questions, let me set up the stage for our final speaker, who is going to speak mostly, right? Are you going to speak remotely or are you here?
I will speak remotely.
Yes. Stop sharing. Yes, the floor is yours. Zizhen, welcome.
Can you see my slide?
Yes.
Okay, so I will talk about LLM as a reranker. So just a little recap. So why do we need a reranker? Because in modern like a retrieval system, we usually use a pipeline approach, and the first stage is usually designed to focus on speed and board recall, like a BM25 to get many candidates. And however, this method is usually quite shallow. For example, they can't capture too much semantic meaning. So we need a second stage that focus on accuracy by re-ranking the candidates from the first stage to have a higher quality result. But why do we use LLM as a re-ranker? Because LLM itself have some inherent advantages. For example, it have a richer comparative reasoning. For example, it can take a set. It can take a set of candidates and directly output an ordering instead of scoring each one independently, like what BERT do. And it also have a stronger effectiveness as a top K result. For example, in some of the common benchmarks, list-wise LLM ranker usually set the SOTA. And it also have a better data efficiency because it can transfer the semantic and the linguistic knowledge. So it can outperform encoder-only models, especially in low data regime. How to rank? So there are usually three strategies. One is point-wise, which give each document a score and then rank. And the second is pairwise, which compare two documents and see which one is better. And the last one is list-wise. So the LLM will be given all the candidates and it will directly output the ranking. And how can LLM be a re-ranker? So we usually adopt two approaches. One is to fine-tune LLM for this re-ranking task. And another one is use zero-shot re-ranking, which use prompt engineering. One approach I want to show is a mono T5. So the idea is not that hard. So the input is a query and a document, and then also it can also be shown here. So it wants the T5 model to generate the target word, either true or false. And the relevance score is calculated by the probability of assigning to true. And they will use this score as a ranking score. And in the training stage, it will use the MS macro as a data set, and which contains 500,000 pairs of queries and relevant documents. And then it will fine-tune the T5 model to predict true or false. And the result is promising. It can surpass some previous model like a BM25 and a BERT model. Moreover, in the robust 04 dataset, the T5 model trained on MS macro can also surpass some BERT-based model like these two and the BM25. So this shows that the LLM as a reranker have a strong generalization ability. Although the mono T5, which we talked about just now, is a breakthrough, but it calculates it considers the re-ranking as a classification problem. So the relevance score is pointwise. So when doing the training, it also doesn't have the ranking loss. So rank T5 want to improve upon this. Rank T5 want to output a score to represent the relevance, and it also wants the model to learn to rank instead of classification. So here showing the picture, we can see that the T5, the rank T5, use a special token, which is extra ID 10, and it will use unnormalized logic as a score. Another difference from the previous mono T5 is that the rank T5 will connect score for many positive and negative documents under the same query and then apply the ranking loss. For example, it will have the pairwise ranking loss. It will punish cases where the negative documents have a higher score than the positive documents. It also have like the leastwise softmax score. So it will softmax the score of documents, and they want the positive documents they want to push the positive document to have a higher score. And then lastly is poly1, which is just an extension from the second softmax method, because it will have this extra term that want to push the positive class to have a higher score. And we can show here with the poly1 loss, it can surpass the mono T5 method, as well as the previously BERT method. And another category of using LLM as a ranking is zero-shot prompting. So the idea is that it will take the passage as input, like passage 1 all the way to passage 10, and then input the query, input the query, and ask the LLM to sort the passage by their relevance to the query, and it will intentionally left this as open to ask to let the LLM to generate the following ranking. And also you use a progressive ranking because usually because we have lots of candidate documents, the candidate length is usually over the context length. So it will take the last M documents, re-rank them, and push the window forward by M over 2 documents, and then re-rank this new group and repeat until to the front of the list. And then it will combine the ranking to get the final ranking. So as shown here, oh, by the way, it used instead of this prompting template, it also have another prompting template, which is pointwise prompting template. And they compare the result of the leastwise prompting with pointwise prompting. And it finds out that the leastwise prompting is better. And it also surpassed the SOTA model or SOTA method at that time. Yeah, and I think that is all for my part.
Any question for Zizhen's presentation? Okay, so maybe I can ask a question for Zizhen. So Zizhen, you have introduced the zero shots counting for reranking. So it is for this week. And in last week we studied in context learning. So do you think it makes sense to curate some in context example for the ranking and better prompt system? Do you think that makes sense, or do you think it's overkills the purpose of zero shots?
I think it makes sense because I also find a few papers they show that if we have give it different prompting on a different scenario, it will improve the result.
Okay, then my further question is that do you think the ability to rank is during the pre-training stage or the other stage you're deploying models?
During the pre-training stage,
or in the subsequent stages, like the model is able to rank, then where do you think this capacity coming from? Yeah, I mean it's an open question. You have feeling free to analyze.
I think after the tuning, it will have the ability.
Okay, so I mean it is in the pre-training stage, right?
Okay.
Yeah, I also have some guess that it could be in the pre-training stage because in the pre-training we're doing the network prediction and model roughly knows like the order of things that has been buried in the parameters model, in the ordering or the temporal orders of stuff, and perhaps it's yes, so it's my guess. Okay, anyone have more questions you want to discuss with our classmates? Still have a few minutes. Or any question for Zizhen or any question for any of our lecturers today? Okay, no question then and earlier today. Let's give some thanks. Great. Okay. So it's the first time we finished early. Thank you so much for joining us online, guys. So we'll see you in 2 weeks of time because next week's the recess. Cheers.
Is there no class next week?
Next week is recess, so we don't have a class.
Okay.
Okay.